Okay, بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Assalamu alaikum everyone. Uh, how are your midterm grades? Satisfied? Yes? No? Okay. So it doesn't get better than this. Okay. Uh, I hope the midterm will be, so the final will be, as easy. I hope. Okay, so we'll see about that. Today, inshallah, we're going to be starting with topic number 4. So we're going to be looking at the stability of mechanical systems. We're going to be looking also at control of mechanical systems. And this will be in particular, we're going to be taking the rigid body. So we took the modeling of the rigid body, and you see how fundamental this is to model robotic systems. And then we're going to be looking at studying the stability and the control of mechanical systems in general. Today's lecture will be a little bit introductory, and we're going to be looking at just defining a lot of notions related to stability and defining equilibrium points. If you took any course on nonlinear analysis or nonlinear systems, some of the stuff should be familiar. Even if you already took that course, there will be the geometric aspect of it. So hopefully you're going to be also learning some stuff. And who never heard about this stuff? So stability of nonlinear systems. Okay, good. So actually, we have actually the majority not knowing about it. Okay, so state space models. Who's familiar with this? Okay, everyone, good. So first, let's start. So the topics of today will be first, we're going to be looking at state space models in general, how we define them. And then we're going to be specializing them to mechanical systems. State space models of mechanical systems, they have more structure that we can actually use. And we're going to be looking at, in general, what do we mean by equilibrium points and different stability notions, and we're going to be taking some examples. So this is what you should be familiar with. This is a generic state space model. So who said they know state space model? Was this what you had in mind or something else? Okay, so sorry? It's an affine, exactly. It's called, this is usually a state space model, but it's a special one in the sense that a more general case of this would be actually a function of x and u. So when we say a function of x and u, we mean a generic function of x and u that could be nonlinear in terms of x and u. However, this one is called a control affine form, where you have a nonlinear function of x, and you have another nonlinear function of x we call g that maps the u to the x dot. And thus, in this type of systems, the control input always appears linearly in the equation. Okay, it's mapped by a nonlinear function, but itself there is no u squared or sine of u or cosine of u and so on and so forth. So we don't have any nonlinear functions of the u itself. It always appears linearly, and this is usually known as a control affine system. You have the state x, where it lives in a state space, capital X. You have the control input u, which lives in a control space, capital U. You have the output y, which lives in a output space, capital Y, okay? So the f of x itself is usually called a drift term, and it characterizes how the system evolves when you don't apply any inputs. So if I actually just put u equal to 0, what am I left with? X dot is equal to f of x, so I have an ordinary differential equation of x by itself. So you just start from x being some initial condition, you'll find it just follows some sort of trajectory. So this is usually how the natural behavior of the system without any control. And the g of x is usually called the input mapping that describes how the input u enters the equation, how it affects the dynamics of the system. And the h of x is the output mapping that describes which parts of the internal states that you actually have as measurements or as observation. So the easiest case that you say that y is equal to x. In that case, h is just the identity map. Okay, it just takes a point x and gives you y is equal to x. In that case, what do we call this kind of system? No, there's no we're not talking about observability. We're talking about you actually are measuring all of the states. You can actually measure. This is usually called a full state feedback. You can measure the full state x, and you can give it back as a feedback. Of course, you don't see any feedback yet, but of course you know that we're talking about the output equation. Why? Not y, the variable, y, why? Why we're talking about the output equation? You see, the output equation doesn't actually affect the dynamics, right? This is not a differential equation of x and u and y. This is just a differential equation of x and u. So if I know u, I already know how x, okay? But why are we talking about this y equation? Exactly, because you measure X through it. Exactly. You usually don't have full access to X. Of course, the H of X here depends on your case, depends on what type of measurements that you have, what type of sensors you have in your dynamical system, what type of measurements you want to consider. So this is usually the H of X. And sometimes I'm not able to actually measure all of X. Sometimes I'm not even able to measure the X's separately. So let's assume, for example, X was X1 and X2 and X3. Sometimes I can measure X1 plus X2, but not each one of them separately. So usually you have a function there of X in general. Okay. And this is what we're going to be using for control. Yes, Mohammed.
They use this affine form, not, for example, including derivatives for U, square, nonlinear U. Why do you think they usually use this?
That's a good question. So so there are two things. Why don't we consider nonlinearities of the U, and why don't we consider derivatives of the U? If you consider derivatives of the U, you can always redefine a control input that appears here, and then actually this control input. So this new control input, let's say it's V, which is related to the derivatives of U. You can actually add the derivatives there as another state, and so on. Okay. For the derivative, exactly. So usually you see here the X dot is the only derivative, that's the only time derivative. You're talking about time derivative, right? Exactly. So in that case, if you have that the U itself is related to maybe some time derivative of another thing, then you're actually talking about some extra dynamics that you're not including here. Usually you call this like the actuator dynamics. Maybe the input itself already has dynamics of its own. So let's say, for example, you assume that U is the input from a motor, but the motor itself already, no, it has dynamics of its own. So you're not including it here, but it's like external. It's another subsystem. Okay. Non-linearities of U, the kind of systems we're going to be looking at, you can always find it has this case. Okay. Yes, you can to some extent you can always do that. Yes, you can always try to figure out. You can play around, and you can call your new, some sort of new input the U and make it enter with a nonlinear map like this. Okay, but for our most of the cases we're going to be dealing with, we'll actually find. So this kind of systems, even though it's a subset of the general class f of X and U, this is actually it's a very big subset. Okay, that actually will do most of the stuff. Okay, with it. Okay. This covers floating bays, robots, fixed bays, UAVs, and so on. Okay. Any questions so far? This is very abstractly. What this should be familiar to you. So this is usually the first, your first exposition to state space models. In that case, f of X is not just any nonlinear function. It's actually a linear map of X. So in the end, there is some sort of A matrix multiplied by X. This is the f of X we're talking about here. And the G of X, okay, in that case, you assume it's a constant. Okay, that is given, it's a constant map given by the B. And the H of X is also a linear function of X. That's some sort of matrix, some matrix C multiplied by X. So this is the X dot equal to AX plus BU, Y equal to CX form. So this is the linear state space. But there's also another thing, another underlying assumption. When you're using this kind of systems, you're assuming that X lives where? In a Euclidean space. You're considering that the state space here is Euclidean, and thus everything is a linear map. I just have A, B, and C, which are linear maps that transform from one vector space to the other. So you have vector space structure, you have a linear, okay, maps. You don't have any time dependence, you don't have any X dependency on A, and so on. But here, the X itself, we did not say anything about it being actually living in a vector space. So in that case, what is the most general case where X can live? So let's go back. The state space, capital X, what kind of structure could it have? A manifold structure, exactly. So X itself can be a manifold. And in that case, F would be a map on the manifold. It would either point on the manifold and give you something back. We're going to look at it. The G of X is also another map on the manifold. The H of X is another map on the manifold. Okay, so this is the generalization of the simple A, B, and C matrices. Is that clear? Okay. Question? Yes.
Do we have always in mechanical system that the input or the control is not affected by the output?
This is after you do control, but the dynamics itself, you don't have an output. If you're just looking about, for example, I have torques as an input for the robot, there is no sensors, right? We're just talking about you apply torques and the robot starts to move. So this is the first equation. The second equation says I'm having this kind of sensors that I want to feed back to to design the controller. So that's another question. So this is usually called the output equation. And on the point of control, so usually when you're designing the controller, in general, it will be some sort of function beta. So we just leave it very general. So some function of beta of y, not of x. Usually it's a function of y. And of course, if you say that I have full state feedback, then y is equal to x. Then you have a function of x there. But in general, just a function of y. And you design, so this is very abstract. I'm not telling you how you can design the controller. What kind of objectives do you have? But usually you design this controller based on certain techniques. For example, you do Lyapunov control. So you design the control, you design this equation based on Lyapunov theory. This is something we're going to be looking at. You design the controller based on some like PID control theory. You design the control law based on some sliding mode, adaptive control, and so on and so forth. These are different techniques. In the end, they're just one function, one big function of y. This is a little bit of an overkill because actually it can even have some dynamics, okay, of y. So that's related to your question. So even the controller itself can have some dynamics into it, but this is just a simplification of it. And you can design this controller such that you do what's known as regulation or stabilization. Same two names for the same thing. Regulation is simply defined that you want x of t to converge to some sort of desired point, some desired state as t goes to infinity, so asymptotically. Or you can want to do trajectory tracking, where you want x of t to follow some sort of x desired as a function of time. And you also want that the x dot follows x d dot as a function of time as t tends to infinity. So these are usually, okay, what you should be familiar with. But something we're going to be looking at also in the course is interaction control. When you have a robot arm and you want this robot arm to draw something on the surface, or grind, or drill a screw, and so on and so forth, you just don't want to have position control or trajectory tracking. You actually want to do interaction. You want to interact with this environment. And how we deal with interaction control is completely different philosophically of how we do stabilization and tracking. Okay, so these are what we're going to be looking at in the coming weeks, inshallah. Okay, that makes sense. Okay, this is just abstractly, you should be familiar with this. Something about how do we design the control law is usually the design of this control system, a design of this control law is usually through analyzing the stability of the closed loop system. And by doing that, this is what we mean by a closed loop system. It's another f, so x dot is equal to another function of x. And this function of x is usually defined as the original f of x, that was the natural drift, the drift term of the system, the g of x multiplied. Here we had the u, but the u itself, we already designed it to be beta of y, where y itself is a function of x. Okay, so in the end, all of this term is actually just a function of x, and we have a closed system, a closed loop system that's only a function of x, and so x dot is evolved. We have a differential equation in terms of x alone. Okay, so by building up this equation, this is how by analyzing its stability, and this is why we're talking about stability in this topic. By analyzing the stability of this kind of system, we're going to be able to design the controller. Okay, so it works both ways. You can propose a controller, plug it in, and try to see whether it's stable or not, or it can work the other way around. You can actually build this equation, leaving the controller open, and you can try to deduce what the controller should look like such that the system is stable. Okay, and this idea of a system being stable, we have to formalize in this lecture, inshallah. Is that clear? Any questions? Okay. So let's take a step back, okay, before going into the details of about the equilibrium points and what do we mean by stability of the system and so on. Let's look at some state space models of mechanical systems. Let's take the mechanical systems that usually you're familiar with, or the stuff that we already covered earlier throughout the course, and let's rewrite it in a state space model. And inshallah, you're going to have at home a bunch of examples that with the homework that you can practice this by yourself. Okay, so let's go to the board. Let's see. So the first thing we're going to be looking at is the, let's start with the pendulum. Let's start with the pendulum. Here it is. Okay. Okay. So let's take this kind of system. So this is a pendulum of mass M, length L, and this is the screw axis around which it's rotating. So let's assume something like this. So this is a theta dot. And also you're applying here at the joint some sort torque tau with some motor, okay? So I have a motor attached to this link. The link is massless. We just have a lumped mass at its end, and we're just actuating it by this motor. Okay, make sense? So the equation of motion of this kind of system, you should be familiar, okay, from basic mechanic courses, that it's ml squared theta double dot plus b theta dot, where we assume b is some friction in the joint, plus the gravity effects, which mgl sine theta is equal to the tau applied on the pendulum. Theta here lives in minus pi to pi, okay? And theta dot, where does theta dot live? If theta lives, between this interval from minus pi to pi, where does theta dot live? R1, exactly, it's R. Okay? Theta dot is the velocity. It can take any values, not just from minus pi to pi. You can have a rad per second. It can be any number from minus infinity to infinity. Okay? But the theta itself is only limited to be from minus pi to pi. Make sense? Okay. So this is the equation of motion. How do we define now the states? So we said that this equation, this is a second order differential equation. And to write it in a state space form, it has to be in terms of first order equations. And thus we need to always define, okay, states as as much as the number of the order that we have here. So if this is second order, we need to define two states for that. The two states will be, what are your choices? Theta and theta dot. So let's assume that x, okay, which is just x1 and x2, will be chosen as theta and theta dot. Okay, make sense? So what is the space, the state space where x lives in?
Minus pi to pi, x.
Minus pi to pi, and times r, exactly. It's the Cartesian product of this space and that space. You agree? You remember when we said about this interval from minus pi to pi that's actually isomorphic to S to the circle? You remember that? So actually this is isomorphic to S1, exactly. Because it's actually just, just a revolute joint. So in the end, we can say that the state space is S1 cross R1. You all agree? Okay. We don't mean, remember, S1 was the x, was the set of x and y, where x squared plus y squared is equal to 1. But we said that this is isomorphic to this interval, okay? So it's isomorphic. It's not actually exactly the same. So we're not saying that theta lives in here and theta dot lives in there. We're actually saying that this is isomorphic to this set. So it's like a manifold, okay? You can still say, it will be completely normal that you say x is this and this. That's completely normal, okay? So I can always say that this is isomorphic to this, but actually, to be precise, x actually is defined as, let me see, let me take this one. Is actually the interval from minus pi to pi cross r. So this is exactly what x is, and this is isomorphic to this guy. Make sense? Okay. So what is the state space model? The state space model will be x dot, okay, which if I have this as x1 and x2, then okay, usually like we write the state space model as some sort of, it's like a tuple. So we just put them in like a column vector format. So we write like x1 dot and x2 dot, right? And now I trust you should be very comfortable with actually that this is the same as this, right? Because this is just, a tuple of numbers written, in a row vector. We're not actually writing it as a column or row vector. We're just putting them next to each other. And here we're just, writing them one after the other. You should be familiar, you should be comfortable with what that means by now. So this is equal to, what is x1 dot equal to? X2, exactly. You all agree? Okay. What about x2 dot? It's equal to theta double dot. So we must rewrite this following equation in the following way. So we can actually rewrite it as minus g over L multiplied by sine of x1, and we have minus b over ml squared multiplied by x2. And then I can have another term, 0 on the top, and 1 over ml squared multiplied by a tau. Tell me if you agree that this second equation, okay, is nothing else than theta double dot equal to everything else there. So check with it with your eyes. If it's not clear, stop me. Make sense? Everyone?
The two book represented theta double dot.
Sorry?
What do you
x2 dot is equal to this line, right? This one plus this term multiplied by tau. And actually, the right-hand side is equal to theta double dot. So if you see theta double dot is equal, so ml squared theta double dot is equal to tau minus b theta dot minus mgl sine theta. And then we divide both sides by ml squared. So the minus b theta dot will become minus b over ml squared on this side. So this is here. So we have here minus b over ml squared multiplied by theta dot, but theta dot is x2, right? So we chose x2 to be theta dot. So this is this term. And we had here on this side, we had tau minus mgl sine theta, where theta is x1. So I have minus mgl sine x1 divided by ml squared. So m with m goes, you have one L up, two L's down. Okay, so only one down remains, and you have the g on the top. So you have g over L minus g over L sine x1. And then you have the tau. It had nothing here, but when we divide both sides by ml squared, it has a 1 over ml squared like this. You all agree? Make sense? So you see everything inside of this stuff, this equation? What does it look like? Some f of x. And this is it a function of x? It's a special case now. In general, it must be a function. It can be a function of x, but here is just some sort of g that's not a function of x. So you see, we rewrote this. We took this dynamic equation, and I showed you here that it's equivalent to x dot is equal to f of x plus g multiplied by tau. Okay. Clear? Okay. So this part, dynamics, and this is the conclusion. Take another example. Sorry? The output depends on your sensors. Okay? You can define the output in many ways. I'll leave that for later. Okay? How do we define the output? When we come to the control part, let's see which case we're going to be looking at. Okay? So let's leave the output for later. So this is just the dynamic equation. X dot equal to f of x plus g of x. Which one? x1, no, x1 lives in minus pi to pi.
That's off, right? Here in this.
In the equation. I'll come back to that point later. Hopefully by the end of the lecture, hopefully. It's part of the agenda of today. But you'll see, this point what you're mentioning will come back. Any more questions? Okay, let's take another example. Should be familiar. The N-link manipulator. What was the dynamic equation of an N-link manipulator? Okay, yeah, for example, this, you have a link, you have another link, and so on and so forth. Okay, what was the dynamic equation? If this was Q1 dot, and this was Q2 dot, what was the equation? How did it look like? M of Q, Q double dot, plus C of Q and Q dot, by Q dot, which we can rewrite it as, some sort of, if you remember, if you watch the MATLAB tutorial videos, you can actually rewrite it as some small C of Q and Q dot. It's just some torques plus G of Q equal to tau. Oops. Equal to tau. Right? So what do we choose as the state here? X1 and X2 as Q and Q dot. Where does Q and Q dot, both of them together, live? Where does Q live? Where does Q live? For an N-link robot? If this is a two-link, if it's an N-link, cross S1, cross X1, what do we call it? We call it N torus. What if you have prismatic joints? What if you have a mix of prismatic and, yeah, then you have, if joint 1 is prismatic and joint 2 is revolute, and so on and so forth. What do we call this? We call it usually a manifold Q, the configuration space, which could be depending on the joints, right? It will in the end isomorphic to some S, so to the torus cross the R's depending on how many prismatic joints and how many revolute joints that you have. We just call all of this Q of the manipulator. Where does Q dot live? What was it called? The tangent space of capital Q at the point Q. If Q is a capital Q is a manifold, then Q dot lives in the tangent space. So where does Q and Q dot both live? Have you ever seen something like this? Does this make sense? No, it's completely wrong. There was a space that actually both of these lived together. It was called the, what was this called? The tangent bundle, exactly. So this was called the tangent bundle, where you take every point and you take its own tangent space and you put them together into one big manifold. You remember that? Okay. So in this case, if Q is an n-dimensional manifold, what about the tangent space? What's the dimension of it? Also n-dimensional. Then what about the state space? X. It was n squared, no? What's the dimension of this? It's actually the dimension of X here, of the state space, is simply 2 times n. It's 2n. It's n q's and n q dots. Make sense? So q1 up to qn and q1 dot up to qn dot. You just put them together and you call this the x1 and x2. Make sense?
Tangent space is Rn.
It's isomorphic to Rn. Yes, it is isomorphic to Rn. It's also isomorphic to Rn. Yes. Okay. Provided that you're using revolute and prismatic joints. If you have more complicated joints, for example, like spherical or non-holomic joints, things become nasty. Okay. But in the simple case that we discussed, the simple kind of robots that we discussed, yes, it's Rn. Absolutely, yes,
But could be
exactly. So how you represent it mathematically is another story, but it will always be TQ though, and this will always be the tangent bundle. Okay? So how does the equation look like? So x1 dot and x2 dot, how do we write them down? So x1 dot will be equal to x2, same. x1 dot is equal to x2. What about x2 dot? It's q double dot, right? So I just need to put everything else and multiply in the end by m inverse, right? So it will look like this. You agree? Make sense? Okay. So what is all of this? F of x. What is this? Because g of x is a function of x. Is it a function of x1 and x2? Only x1. Only x1, right? But, just for simplicity, we just call it as a function of x, okay? So you see here, we had one example where it was not a function of x. Here is a function of only x1. And here, of course, the f of is a function of x1 and x2. So we just say it's a function of x, where x here is defined at both x1 and x2. Make sense? Everyone agrees? Okay. Another example, last one, then you can continue at home. Okay. See, there's actually you started to see there's actually some pattern, right? How mechanical systems look like in a state space form, and we'll come back to that later. Let's look the multi-rotor aerial vehicle. What does the dynamic equation of a multi-rotor aerial vehicle look like? So we have a frame, 0, and we have a frame at the body fixed frame, for example, the B, and the drone looks something like, let's take our drone to be maybe a quadrotor that looks like this. So this is our quadrotor. You all visualize it, so it's a very bad quadrotor, but makes the point, right? Yeah, exactly. Okay. So what is the dynamic equation of this system? First of all, how do you write the equations of motion? Have you seen something like this before? Did we discuss it? No? I'm disappointed. So did we discuss the dynamic equation of a quadrotor? So the dynamic equation of a quadrotor, first of all, is simply just one rigid body flying, right? So what is the equation of motion of a rigid body? It's I multiplied by V dot is equal to add transpose V IV plus the wrench due to control. So this is the wrench of the propellers, the collective one. All of the propellers together, they rotate and they just apply one big wrench on the whole drone, make it to fly. Assuming it's even fully activated or not, then it will appear here in some sort of, in the wrench itself. If it's underactivated, some parts will be 0 there. You cannot activate it. And then we have another equation that describes so this is only velocity, right? What about position or pose? How do we write the equation of a pose? It's h dot v tilde. You remember how the v tilde look like? 4x4 matrix, you multiply by the h, which is another 4x4 matrix. So the h is a 4x4 matrix. And here v, so where does h live? SE3. Where does the twist live? R6, right? In the end, it was in the tilde form, we lived it in the Lie algebra. But when we wrote it as 6 numbers, angular velocity on the top and linear velocity on the bottom, we just said it's in R6. You all agree? So this is the equation. So what is x1 and x2 now? What are our states? How do you choose the states? H and V. Where does it live? So where does, what's the state space? SE3 cross R6. That's actually correct. Can we say that SE3 is isomorphic to R6? Can you find 6 numbers that represents SE3? Yes, you can. We can have 3. You remember what SE3 had? It had the rotation matrix, and it had the psi. The psi is naturally in R3, but the rotation matrix, is it naturally in R3? But I can find 3 small numbers that represent it. What do we call them? Only? No, I can give you 21 different definitions of roll, pitch, and yaw angles. I can give you 21 different ways of defining 3 numbers that locally parameterize a rotation matrix. The most popular one is that you do rotation around the Z, you call it the yaw, then rotation around the Y, you call it the pitch, then rotation around the X, you call it the roll. Yaw, pitch, roll convention. But it's not the only one. Okay? You can have 21 different versions, including that one. Okay. So the R itself, I can locally, but not globally. I can locally represent it by some sort of vector, for 3 angles. And yes, of course, I can say it's R6. But globally or locally, it makes a difference. So can I find 3 numbers, 3 angles that would define all, that would be consistent for all of the values, for all of the manifold? Is it a global? We call this a global chart.
Transform the specific SE3 that you have.
And if you imagine SE3 as some sort of manifold, then you would maybe take a patch here and define a chart into R3. And then you take another patch on SE3, and you say, okay, in another chart I have R3 and so on and so forth. Does this picture ring a bell? When we're talking about a manifold and we have charts that go to Rn, that's exactly the case. Of course, this should be SO3 here. So SO3 was 3-dimensional, and I can map patches of it to R3. One of the coordinate charts there is the Euler angles. All of this stuff we never discussed. I just, it's up for you if you want to really to dive into it. This answers your question. Can we say SE3 is R6? Locally only, but not general. And that was exactly the definition of a manifold. Remember what the definition of a manifold was? It was a space that locally looks like Rn. So it does locally look like Rn, some Rn, but not globally. Not everywhere it is Rn. Okay. So all of this is extra stuff. So if you want to write it down, write it, because I'll delete it. This part at least. Okay. Delete. Okay. So this was our manifold. And remember when we said that V is actually isomorphic to H dot? This equation, I can go back and forth. It's invertible, right? I can give you the H dot, you can tell me, sorry, I can give you the V and you can give me the H dot, or I can give you the H dot and you can give me the V. So it's an invertible equation, which means it's isomorphic to H dot, where H dot lived in the tangent space to SE3, which means actually this is isomorphic to what? The tangent bundle, exactly, of SE3. You see? So that's the pattern, right? So in all 3 examples that we had, and even more, the state space will always be the tangent bundle. It will always be isomorphic to the tangent bundle. Okay. And now let's write the state space equation. Let's write x1 dot. Let's leave x1 dot for a bit. Let's write x2 dot first. So what does x2 dot look like? It's v dot. Inertia inverse multiplied by, it's a function of what? X2, and then we have here I x2. You all agree? Plus the I inverse W. The wrench due to the propellers. You see there's something missing here. Did someone note it? What is missing in this equation? It's actually missing something there. if you simulate this equation, what will happen? So this equation, you see this equation is a function only of x2, right? That's weird, right? Because the previous ones, they were function of x1 also. The wrench due to the propellers only. Here, the input is the input. There's something missing in that rigid body equation. What is it? Gravity. What is the gravity term? You don't see it, right?
Can you add it to the bench?
So gravity, you can think of it as an external force or the gradient of some potential energy. Remember mechanics, gravity, gravitational force is actually minus the gradient of some potential energy function that depends on the edge. Okay, so in the end, actually, gravity is not just a function that goes downwards. Actually, in this case, the gravity term is a function of the rotation matrix. And it's hard to show you why now. Okay, there's no time. That's a function of the rotation matrix. Okay, so the gravity wrench is a function of the rotation matrix.
The propeller, the drone was in some orientation, the gravity would be different.
That makes sense.
Not much.
Because this V is in which frame? In the body frame. And the gravity in the body frame looks different. You're thinking about gravity in the zero frame, but this is an equation in the B frame. So it makes sense now? Okay. So the gravity actually is the missing part here. Okay. And this will be in the homework, inshallah. You're going to be playing around with it. You see that actually gravity here is a function of x1. R is one of the parts of the H matrix where the H is our x1. Okay, so we can say that the gravity is a function of x1 like this, and we multiply all of this by dynamics in the body frame. Absolutely, yes. Does anyone remember what we call this equation? It had a name. What did we call it? Nope. We called it Euler-Poincaré equation. So this is the Euler-Poincaré equation that describes the evolution of a rigid body in the body frame. Okay. What about the first equation? What is actually the first equation? It should be exactly. It should be x1 multiplied by it's not the skew symmetric form. It was the tilde form of the twist, which was a 4x4 matrix that had the skew symmetric omega next to it, the V, and then the zeros on the bottom. So multiplied by, we called it the S tilde of x2, you remember? Something like this, right? For simplicity, let's recall all of this just one function. Let's call it like beta. Okay, let's just call it, this is actually just a function beta of x1 and x2. Okay, you just give me the h and give me the twist alone. I'm gonna take the twist, I'm gonna put it in the tilde form, multiply by the h as a 4x4 matrix, and as an output, I'm gonna get a 4x4 matrix that corresponds to the h dot. All of this is just beta as a function of x1 and x2 for simplicity. Okay. So if you look at this equation, what does it look like? Even though it's it's ugly, of course this looks nicer. This is ugly, but still it is a function of x only, and this is g. It's not a function of x, and you have here the u, and this is the x dot. Make sense? Okay. So all of the systems that we look at are always put into x dot equal to f of x plus g multiplied by the u. Okay. So you need to practice more on this. So we're gonna have, inshallah, some homeworks at home that you can play around with, and just be comfortable to go back and forth between these kind of systems. Yeah. Yes, Fahd. Yes.
X1 is only given the equation because of that.
That's right. You just remove. That's right.
How does that change the dynamics of
Actually, it's no longer a drone. You're actually thinking of maybe like a satellite. You know, it's a rigid body that's only floating, and it's not going to go down. So this is exactly the model of a satellite. Okay, so if you don't have this equation without the gravity, then you're just a satellite. And in this case, the satellite equation, the satellite momentum, actually the second equation was related to the momentum or the evolution of the twist, is depending on itself. It's not depending on the edge, right? So I can solve this differential equation. If you're integrating this, for example, you solve this one, you take the v, you plug it in here, you integrate it, and you get the edge separately. This is what it means, right? You have some sort of structure.
For the gravity, we represented it with the range, right?
Yes, it's a gravity range.
Opposite directions will be range of the propellers.
No, gravity is always pointing downward.
Yes, propellers are going to.
No, the propellers are depending on how. So now you're thinking about a quad rotor, right? The quad rotor has always the propellers pointing upward. But in general, you can have different, looking propellers. You can have 6 propellers for a hexarotor, or for example, the guys that have the fully activated hexarotor in the project, they're going to have the 6 propellers pointing differently. So in the end, the propellers, the wrench, the propeller wrench would be mapped to the individual propeller thrusts by some sort of map. And this is the map that you invert to actually. So usually the standard way of, but if we have a fully activated system, what you can do control is that you can control this equation, assuming that you have full access to the wrench. And then I can take this desired wrench and I can map it to the individual thrusts. And then I apply the individual thrust to the propellers. Okay. You have a question. It's on your tongue, right? What is it?
Same question. Also, what about the tilt? Will it affect the range?
What about the?
Tilting. The tilt of the propellers. Will it affect the range?
Active tilting or passive tilting? Passive tilting. So it's just, you take the propeller and you just make it pointing differently with fixed angles. Yes, the map that goes from the individual thrust to the wrench, to the total wrench, the resultant wrench, will be different. And actually, if you make all of the propellers pointing upward, then this means that some directions here, which actually the horizontal directions, the X and Y, you're not going to be able to affect them. This is actually one of the reasons why the quad rotor cannot move sideways like this. The guys that have the fully activated hexarotor, you'll be able to move it sideways like this. Okay, there's also some videos online for the same drone. The one in the lab, you mean? Because we haven't made it yet to be fully active. Okay, so the guys working on it are doing it. Okay, I'll tell them. Okay, any more questions? Okay, let's go back. Let's see. Okay. Let's go. So now that we're done with the state space models, you need to practice it a little bit more, and you're gonna, as I mentioned, you're gonna have homework. Now let's look at what then the notion of equilibrium points. Equilibrium points. What do we mean by equilibrium points of a dynamical system? So we're gonna be looking now at x dot equal to f of x of t. Okay. F here can be either the open loop system, or it could be the closed loop system. In both cases, we still have an f of x. Okay. So the case that you're familiar with is that X is an Rn, it's a vector space, just Euclidean space. And in that case, X is just, a vector, and X dot is another vector, and F it's a function that eats Rn and gives you Rn. It could be nonlinear. We're not saying it's linear. The linear case, then you can have, if F is linear, if it's a linear function, if it's a linear map, then we can represent F of X as some matrix A multiplied by X, and we call this a linear map, right? So, but this is not the general case. The general case is that, as you've seen, that X is a manifold, X dot is in the tangent space to that manifold, and F itself is a map that eats a point on the manifold and gives you a tangent vector. So every point will give you a vector. So you can imagine it like this. You see here, all of this vector, this is actually f of x. This is actually the f itself. If I start from this initial condition, I'm going to always follow some trajectory. We call it the integral curves of, of this vector field. And then this curve I'm following, always the tangent vectors will be tangent to it. Makes sense, right? It's a tangent vector to a curve. So the path I'm going to follow starting from some initial condition will always be, okay? The tangent vector is always tangent to the trajectory you're going to be following, okay? They're both the same. And this usually we call it an integral curve. So here you see the true geometric nature of f is not simply some map from x from Rn to Rn, as you would imagine it if you just look at it in coordinates. It's actually what we call, it leads to something called a vector field. This makes sense. Have you heard the term vector field before? Vector field is simply a vector at every point in the manifold. And that's what you see visually there. So this is the formal definition of a vector field. Okay, I leave this at home for you to read. Okay, so f itself is a map from the points to x dot. But if you generalize this such that it's valid for all points, then we just lead to the notion of a vector field. The vector field corresponding to f, we're going to be calling it by sigma f. Okay, so this is just what a vector field is. So the solution of the dynamical system simply is given by the integral curves of this vector field. And if we want to do stability analysis now, that simply we can just take the properties of f or this vector field sigma f. And this is something very strong. This happens actually for ODEs alone, not in general, not for general dynamic equation. So PDEs, that we don't have that. Okay, and we're only looking at ODEs here. So the only way for you to know whether the system, how it will evolve, is simply by solving for x of t, right? I have a differential equation, x dot is equal to f of x of t. So if I want to know how it will evolve, I need to solve the equation. Do we usually solve it analytically or numerically? Numerically. Analytical is impossible except for toy problems, right? You know that from calculus. So I have to solve it numerically. So it means I need to simulate it. I need to simulate all possibilities of this system. So it's not practical, right? So, but ODEs, if I have this equation of motion, if this dynamical equation, I can actually just take this f, this vector field, and I can analyze its properties, and I can know exactly whether the system, how it will evolve, okay? And something related to equilibrium points, for example, of the system, and whether they are stable or not, simply by just looking at the properties of f. So this is something very, very strong. It's actually 1-to-1. So the properties of f are equivalent to the properties of the trajectory of the system, x of t. Okay, does that make sense? Yes or no? I know it's a mouthful, but the intuitive idea is the following. You give me a dynamical system, x dot is equal to f of x, okay? And you tell me, I want to study the properties of this system. I tell you, yes, okay. Two people will do, okay, two things. The first one will take this x dot equal to f of x, we'll go to the computer, we'll try to solve all possible ways of how the system will evolve. And then we'll try to say, okay, yes, that, for example, the system properties are this and this and that. For example, it has these equilibrium points, they are stable, they are not stable, and so on and so forth. Okay? The other person will say, okay, no, you know what? Just give me the equation. I'll do some analytical expressions. I'm going to do some analysis. I'm gonna get the same results you get by doing the computer simulation. Okay, so these are the two people. They will both reach the same results. Okay, by saying it like this means that if you give me this equation of motion, okay, and let's say that you already have a controller inside and you want to test whether the controller is stable or not, this means that I can just take the closed loop F and I can do stability analysis to it, and I can tell you whether the controller will be stable or not. Okay, and this is usually actually, this is a fundamental process when we do control designs. You're all systems and control. So whatever type of control you do, you should always provide the analysis that says that the controller is stable. It will work. Maybe it will not work for all cases, but at least from mathematics, you can tell me, for example, you know what, choose this and this gains. For example, any controller has some gains. You tell me, okay, choose these gains and the controller will be stable. If you choose these gains, the control will be unstable. How do you do that? Even without simulation, by analysis. So that's the whole idea. Okay, so just by math. This math part is what we're going to be doing in the coming lectures, and all of this will be related to what's known as Lyapunov theory. Okay, so we're going to be doing that by what's called Lyapunov theory, and usually we do the simulations in the end just to prove the analysis that we get. Okay, if they don't match, there's something wrong with either the simulation or the theory. Okay. Now let's look at some definitions. What do we mean by an equilibrium point of a dynamical system? So if you give me the sigma f, so this vector field corresponding to the equation of motion, or just the f, okay, they're both one-to-one. A point on the manifold, we're going to be calling this point x star down. It's not star up, so it's not related to the dual or something, just x star down. So it's some point. It's in the state space, and we call it an equilibrium point for this vector field only if and only if I plug it in the function f and I get 0. Then we call this an equilibrium point. Make sense? So an equilibrium point is simply a state that if you start at it, what happens? You stay at it for all time. Why is that? Wait, Hamad. If I'm at x star, what happens? F of x will be what? And thus, what is consequently 0 also? The tangent vector x dot will be 0. So x dot, when I integrate x dot equal to 0, what do I get? X of t. X of t will always be equal to the initial condition I started at for all time. So this is intuitively what an equilibrium point is. Make sense? We're going to look at an example in a bit, inshallah. Notions of stability. And here I want to point out, before I tell you about this, there's a huge difference when you move from linear systems to nonlinear systems. And it's the following, that when you had linear systems, in your linear multivariable control, for example, course, when you have a linear system, you usually talk about stability of the system, right? You say, I have a system that's stable. When we go to nonlinear systems, we're not allowed to say that. Why? We talk about stability of equilibrium points. Why is that?
Stable or unstable at specific points, we cannot talk about the global aspect.
So in other words, so what you're saying implies what? How many equilibrium points does a nonlinear system can have? Multiple. What about linear systems? Only one. So linear systems can have only one equilibrium point, and thus if I'm talking about stability of one equilibrium point, it implies stability of the system. But nonlinear systems, they have the property that they have multiple equilibrium points. So I cannot say that the whole system is either stable or unstable, or globally or locally or exponentially, or all of these notions of stability. I can only say that the system near this equilibrium point is stable. The system near that equilibrium point is unstable. So actually, in other words, I'm talking about the equilibrium point itself is either stable or unstable. So what do we mean by this stability? So this notion of stability is the following. So an equilibrium point is said to be stable if the integral curves of the dynamics stay close to it. And close, I put it here between quotations because it's very hard to define it properly. Actually, to define it properly, we need to talk about topology, and we never talked about it. Okay. So, but this is the intuitive picture. You'll find it in all textbooks, right? So imagine that this is a manifold. And this is x dot. X dot here is like the x star, the equilibrium point. I start near it, and afterwards I just keep on roaming around it. Okay? That's the intuitive explanation. And it's unstable if it's not stable. Okay? Which means that I start near an equilibrium point and I do what? I move away from it. I diverge from it. So I don't stay within some sort of region. I'm always going away from it. This is what instability is. And then I have different types of stability now. So this is stable, but only stable without anything. It's just like stable, period. And usually sometimes people call this stable in the sense of Lyapunov. Okay? But it's just, stable. And this is unstable. And now there are better ways of being stable, right? One of them is called locally asymptotically stable. And in this case, first of all, it has to be stable. So you're not allowed to diverge. But not only that, also the integral curves of the vector field will converge to x star whenever you're within some region U. So if you can find some closed region around the equilibrium point that if you start there, you just go to the equilibrium point, we call this locally asymptotically stable. What is the difference now between locally and global? What do you think? If you start from any point, exactly, you just reach the equilibrium point. This is usually would be globally asymptotically stable. What do you think the best one is? Of course, globally asymptotically stable. I'll give you, just before we will go to the example, something very intuitively, how this leads to robotics directly. You take a quad rotor, you make it fly. Okay? So the quad rotor is flying, and the equilibrium point we're talking about is it to be hovering. Okay, so I just have the quad rotor hovering. And then I give it some disturbance. Okay? I give it a small disturbance. Well, forget about disturbance. I make it, so this is the equilibrium point. I make it start from this initial condition. So I give it a small initial error in the orientation. What happens to it? It just converges like this, right? Okay, and then I make the angle a little bit bigger, it goes to it. I make it very big. For example, I flip the drone upside down, and the controller is not able to actually bring it back up. So this is actually, this we call it a locally asymptotically stable. So this we call it locally asymptotically stable. Okay. What about the global asymptotic stability? What about global asymptotic stable? Even if it's upside down, it just flips and goes back up. Yes, exactly. Okay. So in any orientation, the controller will be able to flip the drone and put it back into the equilibrium point. This is the difference between locally asymptotically stable and globally asymptotically stable. Without further details, if you represent orientation by an Euler angle, this is the best you can get, local asymptotic stability. If you represent the orientation by rotation matrices or quaternions, you can get global asymptotic stability. And there is even more to that statement. It's not. Exactly. What I'm saying, that's correct. It depends on the physical capabilities of the system itself, whether it's able to do that or not. For example, a full Boeing 737 will not be able to do that, yes, physically. But even if it can do it, okay, the representation actually can change, okay, what kind of stability notion that you get, okay? So we have 5 minutes. Let's see how much we have. Okay, let's keep that for next time. Okay. Let's keep the case study for next time. But what we're gonna be doing in this case study is that we're gonna be taking the pendulum. We're gonna be calculating the equilibrium points of it. Okay, and we'll just do some simulations for it. But let's leave that for next time. You'll have it in the slides if you want. You can read it at home. It's not really that hard. Okay, but that's it. Any questions? Clear? Okay. جزاكم الله خير.